non credo che sia una luce. No, faccio darmi consumato. Cioè, il Lecture10 lo facciamo con un po' di piso. طب ما خمسين نكبرته وغيره لا بدي اه طب and do we have any questions? More questions? You? Okay. So let's start with the example that I tried to end last time with, and representations of algebraic. So I remind that algebraic group is a group object in the category of algebraic varieties. Now, inside the category of algebraic groups, there is subcategory of fine algebraic groups, which are the group object in the category of affine algebraic varieties, and this is much simpler object a priori, because a affine algebraic variety is a very simple-minded object, just a locus of solutions of systems of polynomial equations, and we can define that the category very simply just maps between two affine varieties. It is maps. Let's say we're working about algebraic over algebraically closed fields, so it's maps of the sets that can be extended to polynomial map between the ambient affine spaces, linear spaces, affine spaces. Affine inside arbitraries. So even if you don't know its category, you can understand its category, and there is a theorem that this category is basically equal. I even don't need to say equivalent or isomorphic because it just there was like full subcategories of this to linear. Here it's a full subcategory, but okay, of course, many different definitions of the category of affine algebraic varieties, and each definition gives you a different category, but these are all categories are equivalent, and the many different definitions. This category, when I say subcategory, means that there is a canonical fully faithful functor of equal itself. Of course, it can be not a subset. But here it basically is, since we define this as a subcategory of this, or if we define this as a subcategory of this, the linear algebraic group are algebraic groups, and that can be embedded as a closed subgroup. So closed subvariety, closed subvariety of affine variety is just something that is defined by some more polynomial equations. So linear algebraic groups are groups which are subgroups of GLN, closed subgroups of GLN, and this. So of course, any GLN itself is affine, so maybe it's not completely obvious from the first glance, because what is GLN are matrices with determinant not equal to 0. So you can say not equal to 0, it's not equal to 0 is not an equation, it's non-equation. I don't want to say inequality because it's not equal, yes. But there is this standard trick. When you want to say the polynomial f is not equal to 0, f of xn, you can artificially add new variable y, and then write quality. And solution of these equations are the same, like the y uniquely determined by x1 to xn, but but it works only when f is not equal to 0. So linear, and so GLN is a affine group, and any subgroup of GLN, closed subgroup of GLN is also a GLN group. And there is a theorem saying that the other way around is also correct. So any affine group can be embedded into the GLN. Not very hard. There is something to prove, of course. So we mainly just do these two categories, but formally what I say now can be also applied to this one. And so if we have a group, we can define the category of F. And so what we write G in the linear representations of G is a collection of group homomorphisms from G to G. So n-dimensional linear representation is a homomorphism basis. And then we have an algebraic group homomorphism. So it has to be given by polynomials and it has to respect the port. And if you have two representations and you know what is the morphism between the representations, like classical affine groups, with D and W, So we have between representations that commute with action of G. Linear. So Web G, so when we talk about algebraic group, we will by default consider only finite dimensional representations. So finite dimensional representations of G, but G is an abelian category of code. We have kernel, we have co-kernel. It's also a tensor category or a monoidal category because we have tensor product. And it's symmetric monoidal category because the tensor product at the end just tensor product vector spaces. So all these together often called tensor category, or abelian plus monoidal structure. Sometimes you require symmetric when you say tensor, sometimes not. So you can say it's symmetric tensor category, but some people will say no, tensor category have to be symmetric. Depending.
The tensor category is abelian.
Abelian monoidal, and sometimes rigid also. Sometimes you require it, sometimes not. This one is rigid. You have dual vector space. So it means then you have the dual representation, just a dual action on the dual vector space. Here maybe one have to be a bit careful. So if you have a map between V and W, then of course you have the dual map from W star to star. So if you have endomorphism of V, then you have the dual map, which is endomorphism of V star. But if you take group representation, V, so the action of V star is not just by the dual maps, because this will not be a representation of G, because this will reverse the order of multiplication. So the action of V star is by the dual map of G inverse. The original action called pi, so this is one explanation why you have to take the inverse. Another explanation that I usually like more, for example, it's less relevant to the case of dual space, it's more relevant just to the case of function space. If you have group G acting on a variance, for example, the real line acting on itself by shift, and you have graph, you have to look the same direction, you have graph of some function. And now I ask you, what does it mean to shift this graph by 5? So to shift a function by 5. So you would assume it's just shifting the function to the right. And this makes sense. Yes, it's the same action on the point. You want to build the function on the graph. But now if you want to write the formulas, you see that there are -5 there. You all know it from high school, yes? You have to write the shift by 5 of f, x of x, is f of x -5. And guys, this makes sense. Also, R is commutative group, so both things are going to be action. But it's clear that this action is like more the coil. And now if you have non-commutative group acting on X, so F shift by G F at point X, so this formula makes much more sense than this formula. On the technical level, if the group is not commutative, one is an action and the other is not. But even if the group is commutative, you kind of understand that this is shifted wrong, that this will be shifted the wrong direction. So here, +5 will be shifted the wrong direction. So functionals, dual space is a space of functionals. So functionals are a special case of functions. So when you act on them, you want to act on like on a function. So you want to put them in the sequence. So this is a nice tensor symmetric category. Now I said that formally what I say is relevant for algebraic groups, but on the level of the essence, it's only relevant for a finite algebraic group or linear algebra. And why? Because if you're talking about the representation of GLN, if this representation has no kernel, it's faithful representation, and then it means that you embed your group inside GLN, so your group is automatically linear. You can ask why it is closed, but it's easy. So, of course, you might consider representations which have kernel, but if some representation have no kernel, then it means that your group is linear. And if all representation will have kernel, then you can consider the joint kernel, like the intersection of all kernel. So in principle, it might be that each particular representation have a kernel, but the intersection not. But this cannot happen in algebraic setting, algebraic geometry. Yes, you cannot have like infinite structure in algebraic varieties. You have Hilbert basis theorem, and Noetherian property of algebraic variety. So anyhow, like basic results from algebraic geometry say that such thing can happen. So the joint kernel is not relevant to us. We can quotient it out. So of course one has to explain why you can quotient algebraic group by subgroup. So you know it in classical group, but when you do it in algebraic group, you have to construct an algebraic structure there, but it's possible, it's known. And then, in fact, all the representation of G are factors through the representation of this quotient. So the category of representation of G is just equivalent to the category of representation of this quotient. And this quotient is going to be linear group because it has effect for representation. So there is no difference in considering category of representation of arbitrary groups and linear. So this is very nice example of tensor category, and it has kind of forgetful functor to vector. And so in this theory, it's called forgetful functor, it's called fiber functor. So some reason, I can say it in some reason for that, but that's called fiber functor. And this fiber functor is faithful. I won't kill morphism between vectors because it's just the same vector space, yes. But like usual forgetful functor, and it's also exact. This is of course not always true for forgetful functors, but here it is true because all the notion of kernel to kernel we can do on the level of vector spaces. Kernel of a morphism of representation is just a kernel of the morphism between vector spaces, and it has the structure of representation. And the same with co-kernel. So this is exact. In general, if we have a tensor category T and functor to vect, so it's called fiber functor if it satisfies this condition. Tensor functor, it is faithful and it's exact. So I think faithfulness almost follows from the exactness. You need basically it will be non-zero or something like this, and then it's enough. Maybe one that's a bit more. Basically, the only condition, but the exactness is a real condition. Okay. Now we can have another example of tensor category based on this example before. Suppose we have sequence of algebraic groups G1, G2, which is mapped to G1, say onto it and perimeter, G3, etc. So any representation of GI give you a representation of all the groups that come afterward. So it means that you have increasing sequence of one embedded into a this is fully faithful functor, yes. Two. And then you can take the direct limit of this category. So we talked about direct limit of categories, so direct limit of colimit, which is a complicated object, but here it's very simple, it's just increasing unit. So by definition, the limit of this category will be objects there will be representation of one of the group GI, which we consider also as representation of all related groups. And now, and this we can just say by definition is a representation of the limit of this. That is calling GI. We can define it to be a rep and the sequence about it. Now, of course, this is not a very good way to formalize things because we don't really care about the sequence. You can erase a couple of guys here and you don't change the sequence. You basically want to consider the limit of this sequence. But then you can ask in what category you consider the limit of this sequence. So this sequence do not have a limit in the category of algebraic groups, because this might be infinite dimensional or infinitely many connected components. So it's not going to have to be algebraic group. So the correct way to do it is to take the limit in, I think the correct way to do it is to take the limit in the category of group schemes. And then we say group schemes that can be obtained as such a limit is called pro-algebraic. But if you don't want to know what is a group scheme and don't want to think about it, you can think about pro-algebraic group as a sequence like this, and you intuitively at least understand that you consider this thing up to some equivalence. So I don't want to define at this point the category of algebraic groups, but you can understand what's going on. And now this category is just union of categories as we saw before. So it also will have a fiber functor to vector. Any object is okay, anyhow, it's representation, and any object is finite dimensional vector space. So when I say vector, I mean of course vector v, yes. Finite dimensional vector spaces. So it's also a tensor category, also rigid category. So what I want to so I want to give some example. I think we discussed last time. For finite groups. For finite groups is basically the same thing when you take limit of finite groups. And then it's very easy to ask where you take the limit. You can take the limit in the category of topological groups. So it kind of transfers into the algebraic theory, and when you mix these two things together, you get algebraic group. So let's take an example. One example you all know, the modulo n. Okay, this is not one sequence. It's sequence, but it's indexed by not by the integer numbers, but it doesn't really matter. You can use that case. Can you? No, probably here you also need to consider sequences which are not necessarily indexed by integer numbers, but what's called filtered ordered sets, so that any two elements have an element which will be larger than both of them. So then we have those prime whenever n bytes n. So we have such a sequence. But if you want to make life easier, you can do we consider it in one prime equal to k. So when we put such a line, it means z modulo the subgroup generated by this. And so this is, so you can take the limit, and the limit that you get here, you will go to the limit will be the integer periodic numbers, and here you will get just the profile completion of z, which is equal to order or anything. And now, what are representations of this guy? Or representations of this guy? So we can consider the absolute group, and then it might have lots of representations. But we remember that this group has topology. And once it has topology, and we're already interested in finite dimensional representation, so if the representation is continuous, then automatically it satisfies much stronger condition than continuity. So what is it satisfies like locally constant? So what is, or maybe let's call it smooth representation. So if G is a profile group, definition, smooth representation of G, finite dimensional reference of G is representation such that it is with the open representation. So this is open neighborhood of identity. Open neighborhood of one. That's all with identity. So continuity, you expect that there will be a small neighborhood that all like with like small automorphisms. But if the group is profinite, continuity, so exercise, like or continuous, right? Is fine. So if the group is profinite, then continuity implies smoothness. It's much stronger condition. So smoothness is, in this case, means just locally constant. That if you vary the element G in the group, then for some neighborhood, it just don't change anything. Then it can jump. So it look weird. So usually we don't used to see locally constant functions. So over R, locally constant functions are all constant. But in profinite groups, because of this topology, profinite smooth basically means that it factors through one of the quotients. Yes, because profinite groups always have a basis for the topology from open subgroups. So this U, I now just said it's a set, but okay, in fact, you even see it immediately if the action given by identity on this U, so it's true also to the subgroup generated by, so it generates an open subgroup, and on this open subgroup, the action is trivial, so it means that the action factors through the quotient by this open subgroup. And the quotient by open subgroup is exactly one of the groups in the sequence that give us our group. So the topology on the profinite group is such that the kernel, so if we have profinite group, is a limit of such a sequence with finite group. So the kernel to of each of the map from the limit to each of the groups is an open sum. So there are lots of open sums. Okay, so smooth representation of finite groups by definition of profinite groups by definition is just a representation of one of its finite quotients. And so in this case, representation theory of profinite groups, generalized representation theory of pro-algebraic groups. And of course, you can ask me, for example, which is, so any profinite group is pro-algebraic, but it's kind of stupid because the quotients are finite groups, which are algebraic groups, but in a stupid way. So you can ask whether I have an example of a pro-algebraic group which is not that stupid. So not that stupid I can give you easily. It's just product of profinite group and algebraic group. But of course, you probably do not really like this answer. So you can probably make some things like A infinity, like the infinite dimensional affine space. There are many versions of infinite dimensional affine space, so you can just take quotients of, so n dimensional affine space is a quotient of n plus 1 dimensional affine space. And then I can take the limit. I don't really know lots of interesting examples. So maybe, yeah, maybe, what? I don't know how to think about GM through the assigned groups. You need to find on the maps, and there's no really on the map. But probably some of the versions for GL thinking might work. I'm just not sure what are these versions. Yes. Yeah. I saw once some versions of GL infinity and limit. I'm not sure whether it works here or not. Maybe one nice thing that you can do for any group, just discrete group gamma, you can take its pro-algebraic completion. It's the same way you can take profinite completion, you can take pro-algebraic completion. So you range over all maps between gamma to G when G is algebraic group, and then take the limiting over this huge diagonal, all homomorphism from gamma to G. So of course it's limit of GIs. Yes, so I runs over all algebraic groups together with the map from gamma to G. So it looks very big, but of course, yeah, the map can be not onto. But because you take the limit, if the map is not onto, it means that there is a smaller group or it can be not onto, but also it can have non-dense image. But if it is, if the image is not dense, so we can take the closure of the image, and then you have this map back to smaller. And so this smaller in the limits, this group will not survive, only this one. So if you have a limit in a category, it's inverse limit, so limit. If the maps are not onto, the things that are not in the image somehow do not survive inside. So this construction that you can do for any group, and it turns out to be rather interesting construction. So for example, if you start with a group SF3, and you take, let's do for SLN now. This goes also for NN, SLNZ, and you take the limit. So if I'm not mistaken, what you get here is very close to the answer, but I think it's just the answer in this case. This product of SLN is EP. So another example of profiling group, you take algebraic group and then take its points over the ring ZP. ZP is a ring, so if you have algebraic group, it's a linear algebraic group, it's given by equations. And SLN ZP is just solution of these equations, is topological group, and as such is profiling.
Sorry, the product is over what?
Product over prime numbers, but also you have here another thing, SLN C, as an algebraic group. Let's say you're working over C, so you're ranging over like the poor algebraic completion of SLNC, you get this. So in one sense, it's not an interesting example, because just product of profile groups is profiling group, and if you can write also as SLN weekend. This is just profiling group times algebraic group, so boring example. But it is interesting because it's kind of, you start with something that didn't know anything about product, and then you got a product. And maybe the most interesting thing about it is that when n is larger than 2, for example for SS3, representation of these groups are just the same as representation of as fine dimensional representation of this group are just the same as fine dimensional representation of SLNZ. So if you want to study fine dimensional representation of SLNZ, which is a hard problem because this is not finite group, not it's finitely generated, but it's not like it's not finite dimensional group in any sense because you don't consider any topology in this, just discrete group. So it's kind of weird object, but if you want to study its representation, it turns out that you can study them in these steps. So these are four finite groups, and this is finite dimensional algebraic group. It's much simpler. So this is a nice thing. It doesn't work for SL2. So for SL2, there are many finite dimensional representations that cannot be related to anything algebraic, or finite. But for SL3,
Alright, could you explain again how you got this?
I just stated the input, but it's not equal. Sorry. Well, so I just state that the full algebraic completion of this group is equal to this. So it's clear that this is full algebraic group. Yes. And it's clear that you have a map from this group to this group. Just which is the group. And in fact, this map is Zariski dense. And so what does it mean Zariski dense? So for any finite quotient it give you, for any algebraic quotient it give you something Zariski dense. So it's clear that you have a map from the full algebraic completion to here. But it's not clear that it's a quality, it is a theorem. So the full algebraic completion is basically you start with any group and you try to make out of it a full algebraic group. So you try to make it to present as a limit, inverse limit of algebraic groups. So you range over all. So you cannot really present the inverse limit because it's not in quality, but you try to approximate it. So you range over all embedding or all maps of your group into algebraic groups. And then you take limit of all these UGI. And the statement is this what you got. So basically any representation of this group, any map of this group to algebraic group, any finite dimensional representation, factor through just know if this is so maybe you need here and larger than 3, I don't know. Larger than 2. Maybe for this equality you need a larger than 2. Now I'm confused. Yeah, let's take n larger than 2. Later, but for n larger than 2, then this is the algebraic completion. And this means that any representation of finite dimensional representation of this group and factor through a finite dimensional representation of this group. So it's in fact given by finite dimensional representation of this group, and finite dimensional representations of this group are rather simple to have. Okay, so maybe I went a little bit too far away because I just wanted to explain what are algebraic groups, and in fact what is a category of representation of a algebraic group. I hope this is clear. Just by definition, if you have such a sequence, you send union of category of representation. So okay. So now theorem of Tanaka. I don't know. I think it's called Tanakian formalism, Tanaka theorem. Is that in a sense this is the only example of tensor continuum, but with more strength. Theorem. Let T be be a abelian, monoidal, symmetric, rigid category with this is small streets, fiber functor from T let's work over C. So it's over any algebraically closed field and with some adaptation for any field. Then so maybe I should write C linear. So C linear category is category such as on the home you have a structure of a C vector space and the composition is bilinear. Then T is equivalent to rep G. Then there is this for G.
This is a faithful functor.
Yeah, fiber functor, so which is faithful exact. So I remind the fiber functor is faithful exact tensor functor. Faithful exact monoidal. Of course, C linear, it's everything over the field. So this is the theorem. I will not say the proof, but I will try to of course linear for finite linear algebraic. So even if we start with some pro linear algebraic. So even if we can start with the category of representation of non-linear algebraic group. I don't know if you know elliptic curves, but elliptic curves have no representations. So this representation is just representation of the trivial group. So you just ignore it. But for it, you always have a linear. For linear. So let's discuss the proof. Not going to prove it. I think. Yeah, so the basic question is how the hell I find an algebraic group starting with nothing with this category. So here's the idea out and so. So we have the functor F. Functor F is object in the category of functors between two categories. So you can consider it automorphisms. And so F is tensor functor, so f of x times y have a nature transformation, nature isomorphism of x, and so y. So now if we have automorphism of f, we have a map like this, but also we have a map like this, map like this. So yeah. So we basically have a map like this. You have tensor list and bifunctor. What?
Automorphism of F, what is the underneath the
Tensor. So now explain what does it mean, tensor automorphism. So if you just have an automorphism of f, you have such a diagram. Maybe I will add to the diagram. So y. Y. Let me explain this diagram. So here we have okay, I don't give the name for this isomorphism, it just follows from the fact that f is a monoidal functor. And here, if we have automorphism of phi here, so this is phi on the object x tensor y. This is, you have here phi on the object x, and then you tensor it, it's a morphism from here to here. Some tensor is bifunctor, so you can tensor morphisms. And so you want this diagram to be commutative. This is what it means for a functor for f itself, or for in general, morphism between two tensor functors. The general morphism, but the tensor morphism. But they kind of respect the tensor structure on the functors, not on the category, but on the functor. So phi have to be a tensor factor. Now there is a lemma, not very hard, but not very interesting. The phi not equal to 0, utilize phi. So if phi is a tensor endomorphism. This is nice to know that you don't really need to require automorphism. You can just say, I want it to be tensor and non-zero. So maybe you need the unity to be. So I think also here we should assume, I don't know where to assume it, that the endomorphism of the unity is the basis. Yeah, otherwise it's not true, because if it's a field but a larger field, you, for example, can get algebraic group over a larger field. But and if it's not a field, then you can get algebraic groups over rings, and it will become more complicated. So I want to assume this, and then this generality endomorphisms are all tensor endomorphisms are automatically automorphism unless there's
when you say automorphism, you mean that there's an
inverse. Okay, so this is a good beginning, because now we got a group. So this object is a group, but for now we just set theoretical group. And this group is the groups whose representation should give us the contiguity. Or they didn't prove it to you, and they even didn't give you an algebraic group structure on this group. So let me try to give algebraic group structure. So what's the algebraic group structure? So there are several ways to define algebraic groups. You can define the algebraic variety together with a product, etc. But there is another way to define algebraic group. You define it as a functor or commutative unital algebras, two groups. So why this is true? Because this is so by definition, we have now definition of what does it mean for group object in a category. It's functor from the opposite category to groups. So the opposite category of affine algebraic variety is commutative unital algebra. Yeah, any affine algebraic variety have commutative unital algebras without importance and finely generated. But I don't care defining a general factor. Because any affine variety has the ring of functions this variety. This is commutative unital algebra. And the other way around, if you have commutative unital algebra without importance and finely generated, you choose generators and you write the relations, and these relations are the equations that define your variety. Or in more abstract language, you take the spectrum of the algebra and get that kind variety. So I just need to define such a functor. So now I have the functor f from my category boom vector. And here I have an algebra A, and I have a functor of tensoring with A from that to A modulus. Yes? And now I can consider the composition. First perform F, then perform tensoring with A. A is commutative in use finitely generated without important. And I can take this functor and take its endomorphism. This also a group. So now I consider this functor A maps to this. This functor, it's still not a group object algebraic variety, but it kind of wants to be a group object algebraic variety. So it's a functor from a affine variety of two groups. Now, the only thing we need to prove, or in order to construct a algebraic group, we need to compose with sets and prove that this is representative. And in fact, it will not be representable because it's a Rosanta. We don't expect it to be a finite group, an algebraic group, but expect it to be a limit of algebraic group. So to prove that it's pro-representable, we can write a limit of symmetries, and each of them is representable, and the limit gives us. And then we basically can go home. So at least not completely, because then we have to prove that our category T is actually the representation of this. This is a bit harder, but basically the idea is that each time you have object in T, or maybe we should stop for a minute. So did you understand the situation now? But we have something which is not an algebraic group yet, but if we will prove that it's representable, it will become algebraic.
The endomorphism of bends of this composition
It's still a set, a group. Endomorphism, or maybe I should write automorphism, which of course tensor. And this is a tensor functor, because tensoring two vector spaces and then tensoring with A is the same like to tensor each of them with A, and then tensor one with the other over A. Yeah, maybe V tensor A times W tensor A, tensoring over A. So here it's a tensor category, but the tensor structure is tensoring over A. So if you know calculus of tensor products, so everything now is monoidal, so you here the tensoring is over C, right? So everything here is commutative, and you can like let's say how do you say it in SEM?
restrict.
No, soкращать. Cancel. Yeah, cancel this. I always say. So when you do tensor product over something, it's like fractions, so you can cancel things.
But we know that for vector spaces, endomorphism for vector space is not a function.
Not a function.
Why in this case, if we send A to endomorphisms of something ish, A would be a function?
It's okay. It's something very different. Yeah. So if you have two algebras, you ask why. If you have A modules, you have A prime. You have A maps to A prime. Okay, maybe I will say the short answer. You have two functors from A modules to A prime modules, restriction and tensor. So you can go both sides. So you don't. So the problem with the endomorphism is that you can't go both sides, and here you can go both sides. Go both sides before. Okay, so what is basically the other picture of the complement? If we have some object X, we can do definitely X, which is a vector space, yes? And we can consider its endomorphism. So this is algebraic group. A very simple algebraic group is GN, yes? And we get a so let's call this thing by some name. We'll call it. Let's call this G. So G is not an algebraic group a priori, but it is a presheaf of algebraic groups. Yes, it's functor to form the category of affine varieties to sets. And this is an actual algebraic group, which also gives you a presheaf like this. So in the category of presheafs, or the category where you live in, you have a map like this. Now this map doesn't have to be isomorphic. Okay, basically usually never isomorphism, right? Let's suppose like we know the answer, like, look at the last page of the book. So say we have some algebraic group. This is endomorphism of vector space, and our category is category of representation of some algebraic group G. So of course this map is not an isomorphism because it's just a homomorphism. But if again we look at the last page of the book, then at least if our category is actually a representation of algebraic group, then for large enough X, for some representation, this map will be an embedding. So kind of it makes sense if we can reconstruct G from here. And what we do in general, we just take the limit of all these guys. And when we take the limit of all these guys, we will get G. So it means that we presented G as a limit of algebraic groups. And indeed, it's not necessarily an actual algebraic group, but it's almost.
How is this defined again?
How is what defined? This map?
Yes.
So G by definition, let's work on level of points, yes? Let's work on the level of C points, just the naive point. So the C points of G, it's the thing that we defined at the beginning, just automorphism of F. So automorphism of F, by definition, for any X, gives us automorphism end of F, of F of X. So it means that we have a map from G to end of F of X. And this corrects on the level of C points, but it also corrects on the level of not end, the odd. Over any. Over anything. Over any. So you have a morphism of functors from here to here. And at least this gives you a map from G. In fact, it's rather easy to see that this gives you an isomorphism G, an inverse limit of X, when X. No, it's not so. It's not so obvious. Sorry. No, I will not type it because it's not that simple. Because there's a problem with it. Because there's like no really. When X range over all objects in X, this is not. We don't get the diagram because taking automorphism is not a fun. Okay, so it's so I will not say this. I just say that we got a map to a group. It's not enough to prove that it's a group. Or we will want to let it be isomorphic. So if the map is, so we can consider the image of this map, and then we get here some closed subgroup. And sometimes we can say that for certain X it will be 1-to-1, and then we can reconcile G, but sometimes not. We know that sometimes not, and then we need to do something else to present G as a. So I don't claim that I will finish the proof, but I just want to give you this idea of how you can principle prove that something is algebraic when you upload or for algebraic when you upload. Just fun. Okay, let's have 10 minutes, 15 minutes break. We'll meet 11:20.
Ci punto punto
Loops, not groups.
בסטיו לוקח איקס שוב.
זאת כרגע נמדוד סתם על גבי ג'ילה, כן? אז בואו ננסה, אז בואו הדבר הראשון שאני רואה, מה זה אומר שמופיעים בין פונקציות, אני צריך להראות לכל חוב לאן G של החוב יבוא לחוב. אני רוצה להראות כאן G של A, A של X, של זאת חבורה אלגברית, ואני יכול לשאול מה זה A נקודות שלה. זאת פשוט החבורה GLN, אז נותנת נתונים ב-A. אני צריך לעשות את זה פה.
אז כאילו, איך זה מוגדר?
איך זה מוגדר? GLN היא חבורה אלגברית.
כן.
זאת GLN, כן? לא אמרת, N זה המימד של F.
כן, אז GLN.
אז מה זה GLN של חוג? זה מטריצות, היה להם הפיכות עם מקדמים בחוג. הפיכות זה אומר שעם הפיכות כמטריצות עם מקדמים בחוג. זאת אומרת, GLNZ למשל, זה עם מטריצות עם מקדם, עם דטרמיננטה פלוס מינוס אחד, כן, לא סתם לא אבנס.
אז כאילו, כל מה שקוראת לנו זה המימד.
טוב, אנחנו רוצים להיות פקטוריאליים, אנחנו לא רוצים לחשוב על זה אבסטרקט, אבל כן, צודק. עד כדי איזומורפיזם, את צודק. אז בואו ניקח את A שווה ל-C. מה זה G של C? G של C זה פשוט איזומורפיזם של אלפא מטורף. ממה זה? זה פשוט אנדומורפיזם מורכבים של F של X. אז ברור שאנדומורפיזם של אלפא מטורף, לכל אובייקט ספציפי נותן לך אנדומורפיזם מורכב. ממש לא כל אנדומורפיזם מורכב מתקבל ככה, צריך לשם תנאים. שהם כאילו מתאימים לגבול ההפוך או יותר מורכב מזה. אז לפחות ל-C את יודעת לאט. אוקיי, ל-A זה לא יותר מסובך. אני יכול להגיד, אבל זה תרגיל.
טוב. לא.
אני קצת בא, באמת, להראות שזה גבול. זה לא סתם צריך להיות גבול, זה צריך להיות גבול. תדייק את זה, כאילו בעצם משהו כמו שלמים, או גלחת פרטמים, או משהו כזה מסודר.
Я думаю, уже достаточно. Я геометрию объектов. Абсолютно. Это серьезно?
מה?
Это серьезно, это объектов? Это просто уже как-то.
כאילו, אתם יכולים לדמיין את זה ככה, E-N, ולקחת איזושהי קבוצה של פולינומים, ולהסתכל על הפתרונות של הפולינומים האלה, E-N, ואז אפשר להגדיר את זה משהו שנקרא טופולוגיית זריסקי, ונגיד שזאת יריעה פנימית, ואז להגדיר גם משך חבילות.
רמי, ביקשת לא לעשות.
מה? לא ביקשתי לא לעשות.
רמי ביקש או כפיר ביקש? צביקה ביקש? לא, הוא רוצה וילונות. לא, הוא רוצה וילונות. כמו שעשית למטה. בנציאני כזה שאתה יכול לשלם.
יש יותר מאופציה אחת שלו. יש יותר מאופציה אחת שלו.
תסתכל אצל עמוס שם, אצל עמוס. תראה את הווילונות, תגיד לי, אני אגיד. אם אתה עושה משהו אחר, הוא יבוא, יצא לך משהו אחר. זה ייקח זמן. בסדר?
אני אסתכל שם אם זה טוב.
הוא יסתכל, הוא יגיד. לא, לא תמיד, אני מדבר על זה. לא, בסדר, טוב. הוא יגיע הפרופסור, הוא יסתכל על מה שעשית למטה, ויגיד הוא טוב, תבוא, תבוא.
פשוט אומר שכל ה-open sets זה כאילו הם open, הם משלים שלהם, כלומר לא סטפ, הוא כל האפסים שיכולים להזדקק פה לאט. מערכת פולינומית מסוימת, יש כמובן סופית שלהם עושים לפולינום אחד, כן, אבל מערכת של פולינום, כאילו נגיד יש פולינום מה-CN מלא משתנים, יש לך מערכת שלו, אז זה כבר יותר חמסילות. יש לך פולינום יחיד ב-C, אז נתן לך חמסות של ב-R. אבל יש לך RM ו-CN, אז כבר תחשוב על אליפסה. באליפס יש שתי נקודות. גם ב-Z לסקת N יש שתי נקודות. אבל עכשיו אני חושב שיש לך אקספוליפור פלוס Y בריבוע. ואז אתה עושה מינוס 2, מוריד את זה, שכל הפסים זה יכולים להעמיד כל פלוס Y בריבוע. לא, זה עכשיו זה אליפסואד. יכול לבוא פלוס Y בריבוע ששווה לאחד. זה מעגל, כל זה דבר שלי. אז יכול להיות בריבוע, סוים בריבוע מינוס אחד. עם כל הפסים שלו. זה מעגל. שניים. זה מסכם. אבל זה כן כאילו לא יודע לך area, יש שם weird shapes. אז תקרא את המשנים שלהם, וגם זה יראה קצת. That's what I said. Overlooking. That's it. Topologia permitting on the house law is absurd. הסמינר שעולה, אני חושב שהיה יום שני שלישי. במובן שם, זאת מישהו מרקע, האם לזה יש לך רקע כאילו? כן, זה יחסית רקע, אבל זה לא יחסית בשביל. אבל זה נחמד, כי נגיד, זה דברים שקשור. כי זה קשור, אם יש לך נויז צ'אנלס, בין שתי שאלה, כאילו אפשר לקודד נויז ומסגור לעצמם, למשל, שיש לך איזשהו אדרס שמאזין לך שם, יודע להפוך על דיפרקשן ביטים, וזה כאילו הכי גבוה, ויש משהו שרון צייר, כאילו כל ביט יש לו הסתברות, כאילו, שהתבלבלות, ואז כאילו כל חסרים למה אפשר לעשות, וכל מיני. אז אני מסתכל בפעם קצת בדיפליישן או אודישן קוד, ומקבל את זה, וכל מיני. חלק יוכל גם את האישה. אין גרסה שיוכל לחלק בלתי. קומפטישן נגמר, נגיד. אוכלי כלומר, שנגיד, אנחנו פרפקט סקיוריטי, בלי איזשהו shared randomness, אם יש לך, כאילו מתמטי. לדעתי בעולם אתה עושה את זה בכל שכל הרסי כל האלה, וערבים מפתחות כאילו שום דבר. אתה משתמש שם שזה לא, קומפטישן נגמר, כאילו. הוא רוורס לשליסים דברים זה כאילו פוסבלי. זה רק אמרו פה לפסם. לא, אני כאילו, לא יודע, ערב פרקשן, כל היחידים שאני מכיר זה המינג, ופשוט להשתמש ברעיון שבכל דומה רעיון. לא, זה לא היה כל קריטית. כאילו, דברים ספציפית, זה דברים חסים לב כמו the best algorithm we can do with this setting has this rate of actual match size to the code message. זה דברים כאלה. אם זה כאילו עד בסרי נגד תשמעו ברביט. כן. טוב. יש שם זה נכון. אבל זה כפירי אם אתה מעביר מידע לרשת, כן? זה לא בעיה של הקונצל. בעיקרון כל צ'אנל אמיתי בעולם הוא לא סובר בגלל את סרי. כן, אבל בגלל נויז. כאילו אין פוקים. Motion sum. וזה גם סבבה. ראית הכי טוב, נגיד במקרה. סלקו. אני שואל. האנטרופיה של צמיחה.
זה בסטנדרט PG. different. זה מap from SRN to PG.
כן, זה כאילו עשית פרוטים.
לא כן.
נראה הקורס שעבר שלקחו בצריך דבר ראשון. זה עכשיו אני עכשיו זה מדע מחשב, זה כאילו זה כאילו יש מדע מחשב סבבה. זה מדעתי הוא ינסה לפני כל משהו
It seems that we have no chance to have Jacob's subtractions on
main applications in most.
PGLN כן לא איבדת או ליניאר גוף PGLN
כמה סטרייט של חולות
не потеряна от группа
מינוס לוג
PGLN,
אבל אני חושב כי נגיד אני חושב שזה דפוס הזה
так же как PGLN это факт жира,
פשוט להגיש דף מלא בשאלות.
Мне кажется, что если он будет цепочкой проекций,
не нужна цепочка, да, это просто сами PGLN просто можно вложить
אבל אני עזרתי למישהו לעשות
наверное, если так цепочкой, то нужно цепочка между
что такое же все матрицы они должны быть где-то конечные, где-то нули.
אני גם נשאר что его отвечать
И то, что они обычно делают, они делают то можно как но есть еще группа посередине. P посередине. Матрица, у которой есть блок тут, делает, скажем, единичку, не очень важно. Еще тут есть что угодно. Эта группа, и если тичер этой группы, то там есть и то, и то. Можно рассматривать такой пример, рассматривать, который
Пример с реактивным пределом можно сказать реактивовольтным отцом.
Не точно будет снять минус. Okay. So we want to continue. So this was not an theorem, and we didn't really prove it, but at least I hope I convince you that it makes sense. But no, okay, maybe. And so one you can ask, okay, if you have a fiber functor, whether it is unique, maybe you can get different fiber functors and representations of different groups will give you the same category. So the idea is that it is essentially unique in the sense that the category of pairs, two categories we didn't discuss yet, of pairs, algebraic group and the five, and sorry, the Naken category with a fiber functor is equivalent to the category, two category of the Naken categories, just all categories that have fiber functor. And now you can ask whether, so now any Naken or any group or any four algebraic group give us the Naken category. So we kind of have a functor from groups to the Naken categories. You can ask whether this functor is equivalence. Because it cannot be equivalence because it's functor from a category to a two category. So we have here or groups. So we have a functor that takes two functors that takes the Naken category is a category, tensor, nodal, all these big words at the beginning together with the five functor. So category that satisfies the conditions at zero. Sorry, I didn't say. So you have a functor like this. So in what sense is a functor? It's this is one category and this is two category. But for any object here, you give a category, and for any morphism between objects here, you give a functor. And now, if you have two groups, and you have the functor is to the opposite direction. It's a quantum variable. You have restriction. And now restriction is always an exact functor in two groups because kernel and co-kernels in fact are even restriction to the trivial group is an exact functor. It's always an exact functor. And it's tensor functor, and it's what else? Tensor monoidal, rigid for the symmetric, so it's preserve all the structure. And then you can ask the other way around. Is it true that if we have two Naken category, T1 and T2, and functor between them, exact tensor whatever, is it true that this functor comes from a morphism between the groups? And the answer is yes, but you have to be careful. So any such functor comes from morphism if it's good, exact, and whatever, comes from morphism between groups, but two different morphisms can give you basically the same functor or isomorphic functor. Because here we see the problem, yes, because this is categories of different morphisms of groups are just different, and here different functors between the Naken categories might be isomorphic. So what does it mean for two different morphisms between groups to give the same functor? So here is an example. If you have G and you have element of G, so you can consider the joint action of this element. So there's any what we mean that a joint action of G give you morphism. What should I say it? Yeah, give you a different functor. So if you have V and you have pi from V to V, now we fix an element, so you can consider pi prime of G equal to first say pi of G And then it's not that sign. And not H. So we put pi of H, and then you conjugate it with pi of G. So we got new representation. So each time you have element of G, you get and the representation, you can get a new representation. So what does it mean? It means that you got functor f from rep, let's call it fg, from rep g to itself. Now this new representation is isomorphic to your original representation, which is kind of stupid, yes, because this gives you the isomorph. So it's isomorphic to your new representation, but it's a different representation. And so you have a isomorphism from identity to for every representation you have isomorphism, so it gives you isomorphism found. And to check of whether it satisfies the requirements to be isomorphism found. So these two functors are different, but they are isomorphic, and the data that defines them. Okay, so now, before we said that if we have, so what's the identity functor? Identity functor is the functor that come from the identity morphism on V to G. And what is the other functor, Fg? Is in fact the functor that came from the morphism at G, from G to G. Yeah, because what's written here? Here is what the same of pi of G, H, G. And so it means that you apply automorphism and then do. So these two morphisms are very different morphisms, but they give the same functors from rep G to rep G. Not same, but isomorphic. So in fact, we can try to define two categories of groups. The object going to be groups, morphisms going to be morphism between groups, but then we can define morphism between morphisms. And this is basically, I think, product with adjunction. So let's say we have two maps from G to H, F and G. So morphism between F and G will be element of H. Do we need the actual element or yeah, I think we need the actual element. I'm not sure. No, probably not. So it should be an inner automorphism of H. But let's start with element of H, such that if you first perform G and then perform add H, you will get G. And so and you need the actual element. So this is a two category. I know I didn't define it. Maybe I will define it later. This is a two category, and the objects are groups. We have a morphism and we have morphism between. Yes, what?
We first have to apply F, then we have to
And this two category is equivalent to the two category of Tanakian category, where the functors between two Tanakian categories are exact tensor functors. And morphism between such functors are just natural transformation. The tensor natural transformation functors, but they're also tensor morphisms, as we saw before when you do these automorphism of the fiber functor. And
Can we do such a trick with a general category? Like we have just a usual category. We want to produce a two category.
I don't know what are inner auto. Like here we use the fact that elements of G, that we have the notion of elements of G, and an element of G gives you automorphism of G by conjugation. something which is very, very much rooted in group theory.
Can we say we just want to consider compositions of morphisms with automorphisms of vectors?
No, but it's not what we do. This you can do, but this I think from we said we not really do inner automorphism. Even not automorphism of functor of target, but
Sorry.
element that defines it or not.
Why
So
is-
the automorphism should be add H. And the morphism is not just the knowledge of who is add H, you need to know who is H. So different H define different morphisms. So they're going from the same object to the same object to second. So this is something very much. So for group theory, you have the category of the two categories of automorphism. So for any two group, say for group in itself, we have the notion of automorphisms. And so morphisms modulo and morphism automorphisms modulo automorphisms that are given by conjugation. And maybe you know this notation out. You know this notation? So out G is by definition this out G divided by in G. In G is inner morphism automorphism G. So the things that come from elements of G. Yeah, I never know how they should pronounce this. I think in English I should pronounce this out G and this out G because automorphism. But other languages say Hebrew this is out G because it's automorphism and this is out G because they want it to be different and this starts with O. So I don't know. This somehow so I don't really know. But this the outer automorphism. So outer automorphism is not a real automorphism. It's automorphism up to multiplication by an inner automorphism. Inner automorphism is a real automorphism, and inner automorphism is given by conjugation. And you have this category, which is better to think about as two categories. So we have object groups, morphisms are just morphisms, and morphism between morphisms are conjugation by such a products by inner automorphisms of the term. And this, so if you consider this category what are automorphism of a group G, so if you just consider that the set is going to be automorphism of the group G, but it's a category, it's an isomorphic object, so you can consider the isomorphism classes here. The isomorphism classes are going to be.
So this two category that you just defined is equivalent to the Tanakian?
Tanakian to the two categories of Tanakian categories when you're careful, when you define correctly what are morphisms between Tanakian categories, which should be functors, but not all the functors, only exact functor, tensor, monoidal, so it's more data, symmetric, whatever, but also they have to be exact. And when you have to be again careful when you define what are morphisms between two such functors. They also have to be tensor functors, so they respect the structures of these directions. And then you can reconstruct this category on like the level of groups. So if you have studied a course in algebraic groups or in Lie algebras, you probably study linking diagrams. And if you have an algebraic group or Lie algebra better, then it might have many automorphisms. But most of them are inner. They're coming from automorphism for element of the group. And if you want to study the outer automorphism of a Lie algebra, it's exactly automorphism of this linking diagram. So and this actually gives you automorphism of the category of representation of the algebraic group. And conjugation doesn't really give you non-trivial automorphism of the category of representation because it just has a more controlled value. Okay. So it's very nice, but now we have a tensor category, nice tensor category, but without Fourier functor. So we kind of know that if we will find Fourier functor, it will be essentially unique. But you still want to ask, okay, how do I know whether I have that Fourier functor or do not have? Some categories do not have, some does have. How do I know? Just by looking at the category itself. And now there are two criteria by D. So, Green theorem. I don't know why the link. Let's create 1.1. We have assume T is a sense of the category. I don't say all the words, but all the conditions before without the file. Metric monoidal, you also then end of identity C, the reaches whatever you want, but you don't have a priori. Such that for any x in T exists n such that lambda n x. I need to explain what that is. So what is lambda n x? So you all know what is vector power symmetric power to tensor power n because it's tensor category. But it's also a symmetric category, so the group Sn acts here. And now I can consider all, I will say something wrong, all the elements here that when you change two things, you get a minus sign. So you can claim that this is wrong, but because there are no elements. But I actually can describe it. Let's do it with n equal to 2. I can describe it as in categorical terms because I have the symmetric, the braiding or the symmetric structure from here to here. Therefore, x and y you have or the braiding, so it's x and x you also have. So you can consider S minus 1. This is an minus identity. This is an additive category. You have identity, you have S, you can take the difference. And it's also, how do you call it? Abelian category. So you consider the kernel of CC. The kernel of CC is the symmetric power. The anti-symmetric scales. No, sorry, I want to take the sum. I want that when you flip plus identity, you get 0, so you can take the sum. So and you can do the same for lambda n. The section of the kernel, so you can define the limit of some diagram. So you can do all that. So this is something that you have in any Tanaka category. But you have a file functor, you get the vector space. You know that any fine dimensional vector space, external power at some point will die. So and once the file functor space, once dead, it's dead. So this is if this is equal to 0, then the interaction category is always satisfied. So what is the theorem? This implies T is implies that you have a file functor. This is a very surprising theorem because in order to prove it, you need to invent out of nowhere with a fiber functor. And I don't know how to do it. I didn't prove, I don't know prove. But you need to prove it, so somehow use this fact to just create from scratch a fiber functor. And this is a very nice criterion. Okay, but this criterion is still kind of hard to verify as you have object X, you don't know what should be this n, how many times you need to take. And then we get an upgrade of this theorem. Let's call it 1.2. What is that? Upgrade? The same, right? The same beginning, but then assume that for any x and t, being x is a natural. So you remember what is the dimension of an object in a modular category? It's a trace of the identity functor, but you just can consider you have identity, make the right star. Everything is symmetric, so I don't care about the directions here. Make identity. So we get endomorphism of identity, and we're working over C now. So in characteristic 0, positive characteristic is become a disaster, but in characteristic 0 it works very well. So let's work over C. We get a complex number. And this complex number, we call it dimension of x, but it might be fractional, it might be negative, it might be non-real. But if for some reason it's always integer, then and this even more surprising theorem. What?
So we don't assume that we have n such that
We don't assume it. We okay, but a posteriori it will be true because for the Nakian category you have. So kind we have now three conditions: to be Nakian, to have vanishing disease, or to have integer dimension. So the clear implication. So here the other implication is clear. Yes. This is easy. But in fact, also this implication. I think that yes, this implication from here to here also different. So all three things are equivalent. Oh, this is not very easy.
How do you say
No.
that?
I will talk about it, but I will not. I will start to prove it now, but probably in the next lesson. I hope today we will complete or almost complete it. So this is not hard. This is not hard on the level that I can explain. I don't know how to reverse this equivalence and how to reverse this. So I think what Deline do in the, at least in the later proof, is just directly prove this theorem, and then this theorem is just stronger version of this theorem. It implies this theorem, and I will try to explain why. So why, if lambda n is equal to 0, then n has an integer dimension. But at least you all can guess what is this integer dimension. More accurately, n minus 1 when n is the first n when it actually happens. Yes. And let me try to explain why it makes sense. Because if we start with representation x, we can try to compute, or not representation of object x, we can try to compute, and we know its dimension. We can try to compute the dimension of lambda n. So let's start with lambda 2x. Do we have a guess what is the dimension of lambda 2x? Any guesses?
Choices go ahead. So it's
Why we know this guess? Because we know what happens in vector space. And in fact, we know this guess for any Tanakian category. Because if we have a Pfeiffer functor, then Pfeiffer functor preserves the dimension. So instead of computing because it tensor and everything, computing the dimension at the beginning, we can compute it at the end, and at the end is vector spaces. We know it for vector spaces. And for the same reason, we guess that lambda nx. Here not x, dx. And x dx. Now, this can be a complex number, yes? But still, it makes sense to just do the same formula. So, binomial coefficient makes sense if the bottom is integer. In fact, it makes sense for any two complex numbers, almost. But if the bottom integer, it's a very nice polynomial on the top. The coefficients are not integers, but we don't really know. So if we assume this fact for any tensor category, or tensor category, then we're done. Because if this is going to be 0, then the dimension has to be 0, because the dimension of 0 is 0. nothing to work. And if the original dimension was not integer, then such product will never be 0. And so in fact, we're not even sure that the dimension is the first n when it happens, but it has to be integer up to smaller than this first n. So if lambda n is equal to 0, then it means the dimension is a natural number which is smaller than the strict. So, but we still didn't prove this thing. It just kind of makes sense. We didn't prove it, so maybe we'll. And so we have these two Deligne theorems, and now there is another Deligne theorem that went to the super world. So you remember the category of super vector spaces? It was a symmetric category, but vector spaces with D2 grading, so vector spaces that are written as V0 plus V1, even part and small part. But this category don't have a fiber functor to vector, because of course have a forget to functor to vector, just takes the vector space, forget the grading. And it respects the tensor product, because the tensor product is going to be tensor product such, but it's not a symmetric functor. It doesn't respect the symmetric structure here. So the symmetric structure here, shift multiply by sign, you probably remember some sign. And so the category of vector spaces is an example of category that does not have a fiber functor, and you can see that it does not have a fiber functor because it's actually a negative dimensional object. It's the dimension of this thing is d0 minus d0. It takes definition of dimension, it's negative, or it might be negative. So this category is not okay, but it's kind of the next best thing. Best thing, you can call it super Tannakian, because it has fiber functor to the category of super vector space. So we can ask, let's classify the super Tannakian categories. Categories that have fiber functor to super vector space. Or Tannakian transfer. And the answer is that basically the same answer, but in the super world. So you have to define super algebraic group. What is super algebraic group? You have to first define what is a super algebra. Super algebra is just algebra objects, a monoid. Yeah, I will explain in a moment what it means. Monoid object in the category of super vector spaces. So you remember we discussed group object and monoid object in general category. But in monoidal categories, there is another notion of group object, or not of group object, monoid object. So instead of doing math from A times A to A, when A just Cartesian product, in monoidal category, we can define different object, different notion, it's actually different, of a group object or monoid object, and then from A tens or A to A. And if the category is just monoidal category, you can define what is monoid object, but we can, sometimes it's called algebra object. So an algebra object, but we can't define commutativity because there is no meaning to switch these two guys. But if we're working in symmetric category, then we have the braiding structure. So if it's braided and not symmetric, you can do it, but you have something usually meaningless. And you can ask this diagram to be commutative. So you have a notion of commutative algebra in your category. So you have the notion of commutative superalgebra. So commutative superalgebra is super vector space with a product, which is not really commutative. It's commutative with respect to this super braiding. And if you write the formula, you see some different things. So even elements have to commute with even elements, even have to commute with odd, but odd with odd anti-commute. Something weird. Sometimes people call it super commutative algebra. So they take the commutativity axiom and change it a little bit to put a super. But probably from this point of view, it's more correct to call it commutative superalgebra. It's just commutative algebra object in the category of superalgebra. So this is commutative superalgebra. And then you can consider the commutative superalgebra with unity. They're all with unity, sorry. And nilpotent free and finely generated, whatever you want. And then you get the notion, and this is equivalent to the opposite category of the category of a affine. So you can define affine super variety, just object in the opposite category to the category of commutative subalgebra. So basically commutative subalgebra. Here we, of course, we allow nilpotence because all the elements want to be nilpotent. So we allow nilpotence, but we can not allow, if we want to, we can disallow nilpotence in the or even part. That's the matter. So schemes or algebra, not different. And then you can consider a group object in this category. And this means that your algebra will have just two products. Yeah? Because another way to think about algebraic groups, so affine algebraic varieties are like algebra functions on them. And the algebraic group have another structure of a product, but it's not really product on your algebra because you have a map from G times G to G. It doesn't give you a map from regular functions here to regular functions here, because taking regular functions is contravariant functor. So affine varieties is equivalent to the opposite category of algebras. So you have, you can consider polynomial on G, and you have map to polynomial here. And this is called bialgebra. So what is super algebraic group is affine algebraic group is a bialgebra, and with two so it has a product, but it also has this co-product. You have to satisfy the group axiom, which is the same axiom but everything in the opposite category. And so it's a monoid object, or in fact group object in the opposite category to category of supercommutative algebras. Commutative superalgebras. And so in classical case, O of G is commutative as an algebra, but this map is not co-commutative. It's not here you can change the two factors and you get something different. In the super world, O of G is not commutative the algebra, but it is commutative as a super algebra. And you also have co-product. And you have the co-unity because the group has unity, so and you have antipod, so you have some additional structures which make it what is called Hopf algebra. So you basically can repeat all the theorem in the super world, and finally you can try to get the first leading theorem. So theorem 2.1 now, leading theorem 2.1. So it's a super leading theorem. Suppose T is tensor category. With all the additional conditions, but with no final functor. And suppose such that for any x in T, now I don't want to ask the exterior power to be 0, because for super vector spaces it's just not true. If you have odd super vector space, then its exterior power going to be the symmetric power of the actual vector space, because what before was antisymmetric becomes now symmetric because everything is in the odd part. And this is never going to vanish. But if you have an odd vector space, then some symmetric power of it going to vanish. So I can say that either symmetric or antisymmetric going to vanish, but this is of course bullshit, because if you have even and odd parts, then neither will vanish. But still you can somehow kill both of them. How you kill both of them? You kill both of them with sure functors. So I will write and I will try to explain. I just want to exist pi in Sn such that the sure functor corresponding to pi of x equal to 0. I will explain, but I'm going to finish. Then P is super tensor. And this is correct. So now I have to explain what it's correct, but you have it's all okay. You have to correctly define what it means super Catalan can. No, this is correct. You have fiber functor. The Tanaka theorem is not exactly correct. So the super. So if you have a fiber functor to that, two super vector spaces, it still doesn't mean is that you are the category of representations of supergroup. You need to modify this category a little bit, and then it will be correct. I not ready to say now what is the modification, but it's really not so important. Maybe I will say it afterwards. Maybe you can basically ignore it. It's not really important. But yes, it is super Tanakian. So what is Schur functor? So you remember what is Schur functors for vector spaces? Everybody remember? So I Paul. We gave the ones they down. So what is the Schur functor for vector spaces? So you have v to the power n, and you have action of Sn. And now you have pi, which is representation of Sn. So you can consider, let's do the correct direction, Om over Sn. Right. This is a vector space. And this is a functor from vector to vector. Start with v, you get mu vector. So if pi is a trivial representation, what would you get here?
Metric power.
Yes. And if it's a one-dimensional sign representation, lambda 0 power. And in the middle, you get other stuff, which kind of can be more dimensional because here, like, if the representation is one-dimensional, so you basically say, I need elements here that satisfy something. And if it's have several dimensions, so you can choose a basis, and you say I need several elements here that have some relations between them. So in principle, the Schur functor can have a larger dimension. And I think it actually happens. So these are the Schur functors. Now, this is a linear algebra. So what happens in any, so if we say a representation of some group, then of course all these pieces are going to be invariant with respect to this group. So everything goes up. What happens in general category? In general category, tensor symmetric category. So you have an action like this, but it's not really clear what does it mean home from a vector space to objects in your category. But since it's finite dimensional vector space, it's not that hard. You just choose a base. It's not a good definition, but let's do it like this. We choose a vector basis of the vector space. And each basis element maps to some vector here. So you have direct sum of many copies of this. And there you have some equations. Each time you see equation, you can just write a kernel of some. So if your category is a billion, you can construct the Schur functor. This was a bad way to do it. So we can see how to find it in a better way. But basically, once you have, so the Schur functor are given by some equations. Once you have equations that are given in terms of your category, you can define it for any billion. And it's given in terms of your category because it's symmetric model. So in any symmetric tensor category and tensor category that we discussed, you can have you have Schur functors. And then this thing makes sense.
So what does it mean that you decide to send the basis of it? Don't have balance.
I don't, but I mimic the answer. So I do it in the category of vector spaces, get some answer, and then mimic it in a category. So category of vector spaces, I can identify it with v to the power n to the additive power d pi, if you choose a vector, or the alpha here, subject to some conditions.
I
And this already can mimic any category. Also, I don't write it like this, but I just write it as kernel of many maps, so limit of some guy. Of course, this is the ugly way to do it because I chose a kernel basis, so there is a way to do it without basis. Yeah, probably the best thing to say what functors is represent, and then just say that this functor is representable because you can choose basis and present that's it. So we have the sure functors, and if they all vanish, then our category is super high. And now we want to have the category del as a theorem, the mean theorem 2.2. What should be this theorem? So what should be the condition in terms of dimensions that will ensure existence of hash function?
Must be integral.
Reasonable answer, integers like the dimension. If you have 5 functors, then all the dimensions are integers because the dimensions of super vector spaces are integers. Bad news, no such theorem. Already good news. So we didn't construct a category with all integer dimensions and without ensure. So
It doesn't exist.
the theorem doesn't exist because the category exists. So I don't know if it's a bad news or good news, but more category is more.
That means 5 functions of spaces.
Then of course the dimensions are integers because 5 functors without dimension. But there is a category that all the dimensions are integers and there's a 5 functor. There is no 5. So we will not discuss the Linz construction. We discuss a neural construction, which I see is kind of more natural of a different category. And we will try to do it more next time. That makes sense. I thought. So until 12:17. בדוגמה שאנחנו כן נדבר עליה, לא של גילים נקודה של
איזה דוגמה?
לקטגוריה שלמים אבל שלא סופר.
לא.
שני קרובי משפחה שלך ועוד אחד.
באמת? אשכרה.
נראה לי אחת משפט, זה הרבה מעבר לדוגמה. כל פעם, תגיד לך משפט. זה מושג זה משפט שאומר מה זה קטגוריה.
Switch to English.
I will do it in the next hour. Here, let's say it. What does it mean to be a fully kind of category with a fixed object of a given dimension? The short answer that there is no such thing, and the long answer that there are many. What does it mean to be a free field? Free field generated by anyone. Now that free field generated by zero elements. It just means the initial object in the category field. And so it's not such thing. But there are many such things. There are many objects that together and play a role of a single initial object. I don't know what the name of this thing, but and now you have the same here.
This kind of formalization of theory of field with one element.
No, if there would be, then it would be initial object. But even if you don't have it, you can just plus cut your fields. You have SP and you have Q. And together they form an initial object or one initial connection. Yeah, I don't know the name. Initial connection.
Is it something related to Arachilov geometry?
No, it's much more elementary. And what I'm going to talk about now is not related to the field, it's just analogy. And the field is just something very elementary. Yes. There is a notion of simple field. A prime field is.
This is probably a stupid question. But could you explain again why we have a super vector space which is odd than the
Yeah, this again. Well, let's do lambda 2. What is
yes.
lambda 2? It's V element in V times of V, of the kernel of identity plus S in V times of V. Yeah, by definition, it's even written here. Huh? This is lambda 2.
I guess you have no, the structure is all different.
The S is different than the S. S is a braided structure, a symmetric structure,
yes.
so it's different than the classical symmetric structure. In this case, it's just minus the classical symmetric structure. So S plus identity is just identity minus the classical S. And the kernel of identity minus the classical S is exactly even tensors. Tensors that not change when you change also the two elements.
Okay.
Which is of dimension n times n plus 1 divided by 2, and not n times n minus 1 divided by 2. And this number
I
vanishes.
see. Okay. Я вот хотел прислать.
Так. Ну, конечно, не запись Шихара, я просто смотрел, там пробежался глазами. Нормально. Но если пришло, что будешь сказал. Вроде Шификейшн был в прошлый раз. Еще. Вечное возвращение.
Нет, он говорил kernel, именно. Что есть проблемы с имиджем.
Можно определять теорию предпушков, теорию пушков, и они не совпадают. Да. Хорошо. Я вот ехал в автобусе и рассмотрел. Я плохо спал, меня разморило, поэтому сидел в повестке. Автобус уснул. Слушал музыку, включил новый альбом. Вдруг и проспал большую часть его. Прослушал песню, но я не запомнил их совершенно. Да, я проснулся на подъезде криков.
Я никогда не сплю в автобусе. Ой.
It's Sean.
А?
We can put Sean Noel. How do you say Sean Noel? No.
Вы делали.
We also, if you don't sleep, we just talk.
But I can't talk to myself.
Or to somebody. And we talked when I remember I was riding from Tel Aviv for forward, and I talked with somebody.
How was your talk?
Okay. And then at some point, I read she left with at some point the speaker said that we are. Можно по-русски он говорит, что он сейчас поддержаем Киясом. Я сейчас спрашиваю его, явно это после Верховного или до? Да нет, до. Продолжаем разговаривать. А потом, когда он говорит, что я уже понял, что явно это до. Ну и потом в итоге ваты не было. Поездом назвали автобус.
Сейчас. Что?
Мы пропустили Раховод, пропустили явно, потому что вы...
Окей.
Потом
Ну,
пропустили.
видишь? Еще хуже.
Да, ты говоришь, что разговаривать с кем-то это еще хуже, чем спать. Так лучше ставить будильник во всяком случае. Даже когда ты с ним разговариваешь.
Может быть, это просто ты, потому что я понимаю.
Нахуй,
Я
бывает,
знаю
только я.
географию.
Не, ну, даже если я бы знал географию в этот момент, я бы пропустил Раховод. Кто явно. На самом деле, мы же отъезжали от Явни, что ты просто не...
Я периодически взглянул на навигатор просто и видел, что еще не приехали, еще не приехали, вот уже прикольно.
В принципе, я разговариваю, что... Я один раз в Германии, мы ехали в Вольфа, первый вариант, пропустили, потом поехали до последней станции, поехал обратно, и тогда я заснул. И что, тот человек, с которым я разговаривал, всегда достаточно, как, да, если это что-то стандартное. Да, один раз я пропустил самолет, когда просто делал, ну, шаг, гейт, ну, в лоте. Я ступил, что-то делал. Там час получил.
И тебя просто посадили.
Да, ну, это, наверное, пойдет в Америке.
Окей. Интересно.
У нас же они обычно зовут еще, откуда
Да.
кого они зовут, все быстро.
Зовут по именам, по группе связи.
Да, но это когда большие полеты, а это было там, ну, не, Нью-Йорк, или Бостон, нет, да, ну, не помню, но это был какой-то, ну, там, полет, кого-то.
Да, там настоящий анимат. И вот здесь.
Есть вообще.
Еще не да, есть. И год назад там в России. Через 2 недели. 23.
Да. Когда семестр кончится?
Ну, наверное, да. Чтобы задумался докладом по сети.
И что?
Я не сделал доклад по сети.
Ну,
Чтобы разобраться в статье. Вот на проекте. Мне показалось, я понял мысль, потом я нашел некоторое несоответствие с тем, что я думаю, тем, что написано. Я так и не смог себе объяснить. И в итоге все просто отлично.
ничего.
У
А?
тебя еще полно других. Поэтому много.
Ну, еще и... Ты же так знаешь,
Он да.
это принципе, ты пойдешь на...
Более того, с точки зрения вопроса, и логическое прочтение,
Окей.
которое что-то слышал, но я никогда не учил.
Знаешь, как сказал, я хочу в следующий семестр взять
Okay. So now I want to construct a button issue. שנייה. אמרנו 17 דקות? יש עוד דקה.
Yeah. Chose the sheets and so sheets of there. Course chakra.
גרי קוד שחר. גרי קוד שחר. ושאין את כל זה.
Потому что они пересекают.
לימדנו אותך? שם פרסקטה?
Дивно тоже. Это я сказала время. Я сказала тебе, совершенно видео. Так получается, что тогда будет 6 часов подряд. А 6 часов подряд, поэтому такое, что чувствую.
Окей.
Выбери так, чтобы у тебя был глубокий день.
So how do we construct tensor categories? So before we talked about braided categories and symmetric categories, but without a Boolean structure, and then we discussed three categories. And basically we can try to do the same here. Now we can ask what is, so we before ask what is free symmetric rigid category. And you remember that object was points with arrows, and morphisms was just combinatorial passes like this, but respect the arrows. And we don't care about intersection because we symmetric words, so no braiding, everything. But we also can go like this, and we also can do loops. And we can just call the loop by some name T. Better? So we can say we don't have loops, but now we can multiply by C instead. So now if you want to do additive category, or Q linear category, or C linear category, free C linear category generated symmetric coordinate free C linear category generated by one object. So this is very simple. I think this is called raw category. Let's call it B, the graphic no. So objects are like here. No, objects are not like here. Oh, because it should be additive category. So objects are direct sum of objects like here. And morphisms between two objects like here is linear span of such diagrams. And linear over C to C of T over the ring of polynomials in one variable because we have so formal combination. And if we have direct sums, so what is the map between one direct sum to another direct sum is basically a matrix of maps. So if we have direct sum of simple, I don't know, I'm not calling simple object, but nice object Vi, so Vj and direct sum of Vj, and home like this. Direct sum, home the I. Yeah, because this was a home is linear with respect to that sum, so and takes that sum out and get. And how you compose them, basically a matrix multiplication, so you know how to compose each block separately and just you know how to compose it. So this is switch. So this is a very simple category, it's additive category, but it's not a big one. So you can think you can expect that and maybe when we want to generate free abelian category, we just need to add all the kernels and okay. And the thing is, it doesn't work. And what does it mean it doesn't work? So what is a free category? Free category is initial object in some two category or category. And nobody guarantees that initial object will exist. If you work in abelian world, then usually you expect no initial objects. And maybe the intuition coming from the category of fields. So the category of fields do not have initial object. And why do not have initial object? Because you have FP and you have Q and no morphisms between them. So you can't have fields that will map to anything because to any other field because if we have different characteristics are normal. And what you do have in this case you have collection of objects, in this case F point Q, such as any for any other field MK, there only for one of them there will be morphism, and this morphism going to be unique. So there exists a unique morphism from this collection. And this kind of typical in many categories, and you don't have initial objects, you have collection of objects that say together initial object. I don't know the name of the phenomenon, I'm sure there is some name. And in the abelian world, you often have such things. But before, so yeah, you can in general ask, you have an additive category and you want to make out of it a abelian category. So take the free abelian category generated into it. So you have some additive category C, and you want another additive category A and functor to it, additive functor, such that this will be initial out of all such layers. And usually there is no such thing, but often there is some collection of things together. And yeah, I will not give now an example, I will give you some time. But what you can do in general, so additive abelian category means that you kind of have to add all the kernels. Kernels are complicated because things are not exact, so kernels. Okay, maybe I don't have a very simple explanation why it's complicated, but I do have explanation when kernels become much simpler. So if you have a map from X to X itself, which is idempotent, then kernel of this map is much simpler notion. So we have A from P to X and 3 squared equal to so this following. So in this case, the kernel of Phi is much simpler object than in the general. Why? Say our category either again. So we can consider kernel of Phi and consider kernel of 1 X. Then and the statement is that for a given category, you always have a canonical position into that. And you know it in linear algebra, yes, if you have a such as a squared is equal to a, and then it's the space is a sum of the image of A and the kernel of A. And the image of A is exactly the kernel of identity. So this is exercise for any given category. So if our category is not abelian, we still can ask that idempotents will have kernels. And if they have kernels, they also have co-kernels, and you have such nice position, etc. And so category that satisfies this, two names. There is one like sensical name, called think idempotently closed or idempotently complete category. But there's also historical name, mathematician Karoubi that studied this thing, so we can call them Karoubian category. So Shachar told me, don't tell them Karoubian category, nobody uses this name anymore. But it's still much shorter than idempotently closed, or idempotently complete, so I kind of prefer it, Karoubian category. And the good thing about Karoubian category is that any additive category have a Karoubization or idempotent completion. So if you start with additive category, and you consider a category of, I don't know how to call it, functors to Karoubian categories, additive functors Karoubian categories, this category of diagram have an initial object, this two category, and this is called the Karoubization of idempotent completions.
Would you say explicitly what is a Karoubian category?
Category, additive category, where all idempotents have kernels. I think this already once kernels or for kernels, and because just kernels are. And you have the compositions where some like this, so I think this definition I'm not 100% sure. I don't think you need this the second axiom about if the kernel is your identity, so I think for then it's isomorphism. Oh sorry, let's say image isomorphism for image. I don't think you need all of this because once that sum, so everything becomes much simpler. So every category have Karoubization, so every category you can add artificially the kernels of idempotent object. So you basically consider pairs object and idempotent on it, and you think of it as a kernel, and then you have to put some installation, in fact, add some morphisms, and then get the coefficient. So in the okay, so if we start with we have this Bauer category, and now we have to decide what we're going to do with T. Now, the Bauer category itself, we don't really like it because the endomorphism of the identity functor are not C anymore. It's C of T. Oh, not the identity functor, endomorphism of the identity object, yes. But not C. So, and one way is to take Bauer category modulo E equal to some number D. So you just put additional equivalent relation that basically states that your generating object is of dimension. Another way is still use a D, but then you want to make it a field. So you tensor everything, all the homomorphic spaces, with rational functions over T, so you basically invert all the polynomials. And in fact, you don't really. But okay, it's something that you can do. So it's a Bauer category over tensor with C of T, C of T, so over C of T. So I don't explain this notation in general, but here it just means that the homomorphism spaces, which are all modules over this algebra in the Bauer category, because endomorphism of one is this algebra, you tensor them with this, and then so in both cases you get something over here. But in fact, you can even take the Bauer category itself, and each of these categories you can take its Karoubian envelope or Karoubization, or which is a Karoubian category. It's not abelian in general, or it's not necessarily abelian, but you can do it. So when I say it's not necessarily abelian, so in fact here it is abelian. I think for in this case, for C of T is not abelian. And in this case, it's abelian if and only if D is not an integer. If D is an integer, then it's not abelian. Karoubian, so you see the initial work, but in other cases you get something else. I don't prove it, it's not an exercise in any sense, probably not very hard. Okay, all of this gives us something very nice. So you remember I had the depth. Oh, the depth is still here. This is the depth. I didn't do it, yes? So now we can prove it or at least reduce it to some other statement which looks more natural. So
Could you spell Gaussian?
spell Gaussian or you can't spell anything, yes, certainly not Gaussian.
How to Google it?
Try it, it wasn't closed and it wasn't complete. But try to spell it. Or ask ChatGPT what's the name of a category that's identified. That's an important set doesn't tell us. So in NLab it will probably be called like why not closed it? I didn't like. So I have this depth and I have the shoe functors. Now I claim that the shoe functors are in fact find not only on the abelian categories, but also any covariant categories, as long as it's Q linear. So obviously it doesn't work, but if you not just add it also Q linear, then it works. Why? So I said that say lambda 2 is a kernel of S plus identical. And S2 is kernel of S minus 2. Those two guys are not idempotent. But if we divide each of these guys by 2, then they become idempotent. And you know, yeah, you know that you can project to the space of even vectors. You just take your vector plus its flip divided by 2. So any function can be written as the sum of an even function and odd function. You probably studied it in high school. And it's something very general for any representation of S2. So if you move a group of 2 elements, any representation decompose to part which is trivial, where the action of S2 is trivial, and part where the action of S2 is minus. And more generally in Sn, any representation over Q decomposed to direct sum of reducible representations. So these two things are important. You just see it when you square them. You see the formula S square, which is identity because it's symmetric. Identity square, which is identity, minus plus twice S. Why do we get plus twice S? And then we divide everything by 2 and see we get the same. And the same thing. And this is true for S2, and it's true also for Sn. So in Sn acting on x to the power n, or in fact any representation in any category. So we have a notion of representation in a category of Sn is a group, so we have this notion. So of Sn we can find an idempotent, but it probably will not be from this to itself. It will be some something a bit larger. So first of all, we have idempotent from. Sorry, I'm not prepared to talk about it correctly now, so I will not do it. So we can stick with these two, but in fact we can do it for initial functor. But with these two, you see that you can define lambda n. You can define lambda n as a kernel of some idempotent. So in any Caribbean category, you can define lambda. So in fact, you can do it for initial functor. Some time to think about it. Sorry. But for lambda n, you see it. You just take sum of sigma arrangement n of sigma divided by any permutation gives you automorphism of x to the n. Sorry, sigma times unit times sine sigma, or you don't need. I think you don't need. No, let's do times sine sigma. So the image of this thing going to be antisymmetric. The kernel is something else, but the image is antisymmetric. So now if this is idempotent, we can take 1 minus this idempotent, and then the kernel going to be antisymmetric, going to be lambda n. So the kernel of this thing is equal to lambda n. When sigma means sigma for x to the n. So sigma is, let's call it show of sigma. Show of sigma is morphism like this when sigma is from. So lambda n of x, here is definition lambda n of x. Well,
Sorry, what is written after
kernel
sum?
sigma times the sign of sigma. Times sigma is a number, sigma is a morphism, you can sum them all up. I can do this
Then you divide by n.
by n factorial. And then it becomes an idempotent because it's just a projection to the antisymmetric elements. So once you're antisymmetric, when you do these things, then you just get an n factorial times vector. And then if you have a vector which is already antisymmetric, so if you're already in the kernel, then all of this thing. No, so if you're in the image, then show sigma is just equal to the vector itself times sign, and then you take the sign square. It's 1, so you get the vector itself n factorial times, and then you write n factorial again. So this is an idempotent in any category, and you can consider its image or the kernel of this thing, and this is the. So now we're happy, and you see that it works only over Q. It doesn't work because it's characteristic. It doesn't work over Z, but we don't really care. And this allows you already to define. Let's call this category rep. It's a weird name, I know. GLE. Let's call it like this. So for any T, we can consider the free category generated by one object of dimension T, a free Karoubian monoidal, symmetric monoidal rigid category generated by one object of dimension. You can do it when T is symbol. You can do it when T is symbol here. You can do it when T is just a symbol here, so it doesn't have to be invertible. And you can do it with when T is a number.
It's free Karoubian monoidal rigid symmetric.
Okay.
Dimension T.
I'm sorry, could you once again write down all the construction of this category?
This category, in fact, I wrote here. So the Bauer is a combination of either the Bauer category or this category or this category, depending on how you think about T. So if T is an actual number, then T is then you have to work here. If T is a parameter, so if it's parameter here, then you can work in the Bauer category. If it's parameter here, then you have to. So if it's a rational function, then you take the computation.
Again, what is a P capital?
Capital G is a Bauer category, and so the object. So it's a free category without a free additive category, or with one symmetric with one object and rigid. So it means that the objects are direct sums of
Such arrays?
arrays of errors, and morphisms for array of errors are formal combination of type D errors. And for direct sum of formal combination of such data. And now you can take the computation and you get this back. And here you have the show functors. Right? If you walk over C or over Q, you have the show functors. Yes?
Sorry, this tensor product, it's tensor product with polynomials or
Well, with rational functions over polynomials, but I don't explain what is tensor product of a category with an algebra, and I don't want to explain in general, I'm not even sure it makes sense. I just, in this case, it makes sense because the endomorphism of identity of the identity object is this thing. So all the objects are models of this field thing, and then you can tensor them. All the homes are models of this thing, and then we can tensor them. Okay, so in this category you have sure functors. Yes. Now this category is a universal category generated by one object. So now you have your favorite category T and an object X. You have a functor like this. Yes. And you have my favorite category.
Wait, how is it? Why do you fix X? Not fix the X. It is the generator.
Yes. No, here there is a generator.
Yes. So
Here there is no. Here I don't need a generator. I just need an object. Here, so
the
compare.
generator is mapped
Just
to
a-
the
What does it mean? A free category generated by one object. It means that for any pair of category and object, there is a unique after something functor like this. Yeah, because well, it's free group generated by one element, and each time you fix a group and element, then you can make the generator to your. So I have this thing. For general T, I don't have anything else good. So just if dimension of X is T, I have this. So now I want to compute the dimension of the sure functor of X. So tensor functor, symmetric tensor functor have to commute with sure functors. Exact symmetric tensor functor. Everything is here it's not exact, but it preserves kernel and co-kernel of idempotent. So it has to commute. No, this is automatic because it's additive functor preserve direct sums. Kernel of idempotent in the compilation of direct sum. So it has to compute and preserve sure functors. And it also preserves the dimension. So instead of computing the dimension here, I can compute the dimension here of the generator, of the sure functor of the generator. But I have no idea how to do it for general T. But if T equal to N, I have here a very nice category, and rep GLN. Actual representations of GLN. Representation of GLN have a generator. So every representation is a direct summand of tensor power of the standard representation and its dual. So you take the standard representation to some powers times the dual representation to some other power, and then you can cover all the representations. But in fact, you don't even need to know the generator, you just need to know that there is an object, the standard representation, and then you have a functor like this. Yeah, in fact, you probably could just take here vect. Maybe we'll take here vect. Because there is a functor from here to vect. So we can just forget about this little functors. Here I know to compute the dimension of the sure functors, the vector spaces. Yes. And the sure functor preserves dimension. So I also know to compute, so here T equal to N. So I also know how to compute the dimension of sure functors here. So at least in the case when the dimension is integer, I know how to compute the dimension of the sure functor of any object.
So this T is a trace of canonical map from one to one.
Well, now there is no T anymore. Now there's N. Yes, but yes.
Previously.
Previously, yes. Yes, this is. It's free category subject to these conditions, and the trace of the metric just. In broad category, the dimension is T, but T is just a symbol. Yes, it doesn't have any meaning. But when you take some quotients, then we just postulate that T is equal to some number. And if T is equal to an integer number, and then the dimension here equal to the dimension here. So in fact, we already complete our depth, because we just needed to prove that if the dimension is integer, no, we didn't. But if t is integer, we already prove that we know how to compute the dimension of the symmetric power or any other Schur factor. Yeah, because we can take it here. We can compute it here because it's the same like here, and then it's the same like here. And this is only here and object. Now, if t is not integer, so let's go to the Brouwer category. Then what kind of object will, so we have the generator of the Brouwer category. We are generated by one object x. So what kind of object is the dimension of x? Is it a number? In general, the dimension of an object in symmetric in monoid category, rigid monoid category, what kind of object?
It's a functor.
It's not a factor, it's a morphism.
It's
It's
a-
endomorphism of whom?
One.
Of identity. One. Makes an element in N1. And in Brouwer category, what can you say about N1?
It's C of D.
This is a polynomial in T. So in the Brouwer category and also in this globalization, the dimension of the identity of any object, or generating object, but any other object also, is a polynomial of T. So what happens when we map, we have a functor from this category to this category? The objects are the same, and just proportion, we take morphism up to equivalence relation and just calculate the T. So I said that tensor functors preserve dimension, but it's not abundant too. It's true only if the endomorphism of the identity element is just a set, it's just a base field. But here the endomorphism of identity element is not offensive. Okay. But what do we have? We have a map from this thing to the endomorphism of the identity morphism object here, which is C. And the functors, the exact functors preserve no, that you don't need exact, just additive and tensor functor. They preserve dimension in the sense that they map the dimension to the corresponding dimension in the time. Which means that they map a polynomial into
Yeah, graduation.
the evaluation at point. So now we ask now we'll go back to this. I don't want to do this dissertation now. The correlation, maybe C, I don't know, of B of the Brouwer category, of the general Brouwer category. So I'm not working over the field of rational rational
Ski.
what? K? Of rational functions over the ring of polynomials. And I consider the dimension of lambda n of x. And this is a polynomial in a variable t. Let's take x to be the generator. So this is a polynomial in t. And I don't know what is this polynomial. But what do I know? I know its specialization of in any integer number. So I know that for any integer number, so this is equal to some f of t, which I don't know. But f of n, no, not n. Okay, no, let's do here. Okay. F of n equal to n times n minus k plus 1 divided by k plus 1. So now I still don't know the polynomial. Now I do know the polynomial, because if I know its values are all integers, I know it has to be this. So in this category, the correlation of B, I know the dimension as a polynomial. So it means that in any specialization for any D, any complex D, it has to be given by the same formula. And so in any category, if I know the dimension of an object, say it's complex number, then it has to also be given by that formula. So it's kind of indirect proof, but I don't know other proofs. Probably historically there were other proofs because this idea of taking cohabitation of these categories kind of later. Maybe not so much later. But
Sorry, but what was the statement?
that the dimension of stereo powers of any object can be expressed via the dimension of the object with the formula that you know, the binomial coefficient. It's up there.
Just yeah, okay.
And we prove it by proving it first in the category of vector spaces, then deducing it to some free Gaussian category, then deducing for any category but only for elements with integer dimension, and then proving it like in the free category, like on the formal level, polynomials, and getting the polynomial which have to be this, and then again you can specify into it and very long. No, not very long, but very direct. Okay, but we wanted a Abelian category. And 3 Abelian categories generated by a single object of a given image. Is there such a thing? So if the dimension is a parameter in a field of rational functions, then there is such a thing. If the parameter dimension is complex, there's also such a thing. But in general, if the dimension, so rep GLN, rep tilde GLN, which is this category we define, the cohabitization of the broad category subject to the relation that the dimension of the generating object is n. This category is not Abelian. But it is Gaussian and it is free, so it has a functor to rep GLN, because in rep GLN it's also a category which is Abelian in this case, instead of Gaussian, and it have it's in fact generated, but you don't really need to know it. It have an object, a marked object of dimension n, the type of representation, so you have functor. So it's kind of a good candidate for being the Abelian envelope, so the initial object. Yes.
Again, what are we looking for?
Free Abelian category generated three tens of Abelian category generated by a single object of dimension. So this kind of good candidate, so you would think that maybe you were done, but you were ahead. You could see. Oh, no, don't think so. No. But the problem is that there are other good candidates. G L n plus 1 1. So you remember that there is a notion of representation of a supergroup, and there is this nice supergroup GL n plus 1 1. I don't give you the full definition, but like GLN is endomorphism of a vector space, GLMN is endomorphism of a super vector space at all, even part of dimension m and all part of dimension. And this super vector space that generate like the standard object in this category of dimension m minus n, in this case 1. So it's also a Abelian category, also very nice. So in fact, we need to do some modification here. Okay, let's forget about it. So it's also very nice. And then more generally, GL plus K so any two integers with different natural numbers with difference n will and
How is it called again, this object?
the general linear supergroup. GLN, I will call GLN. We call it GLN, yes, or GLMN. So we call it GLMN. But if you want to call it verbally, GLN is a general linear group. It's called GL. So this is a general linear supergroup. So we have infinite many candidates. And now Now I want to give some much more simple example. What is the initial object in the category field? So I didn't say it in the I say it in the break, yes? So the category fields doesn't have an initial object, you know. Because fields of different characteristics don't have map one to the other, so you can't have initial object. What you have instead, you have this collection of FP and Q. And any field have a unique map from exactly one of those types. So maybe we can be very happy and say maybe any abelian category with one object of dimension D have a unique functor, unique up to item of course, and up to unique up to item from one of these guys. But this will not work because these guys are in this analogy kind of behave like this. There should be another guy. So here is theorem of in and Vladimir Finich and Vera Sultanova. So only two of them are members of my family. So Vera Sultanova, I just I don't know why she's there. I think you saw him 2 weeks ago. And with my wife. And so the theorem that there exists category this category A, neighborhood. Oh, and to call it, let's call it a billion category. So then a billion then call that words. And the functor. And the functor from array is G 2. Okay? Such that for any category equal then so or the words before with x in C of dimension n such as for any such thing there exists element E in the set rect GL and N, and there is some modification here, ignore it. MK, sorry, with an escape N or A exists uniquely. It's such as they exist in the unique. It's not exactly an exception to band. Tensor C form what form E to C is the and all the others will not have functors. So there is one more category that you can add here, and such that any functor factorize exactly on one. And in particular, since A is generated by an object of dimension n, it's not obvious. The idea is that I think this category don't add any additional objects. So in particular, all the dimensions are integers. And so we get an example of category with all dimensions integers and does not have any 5 functors because it cannot have 5 functors to here because it already has functor to itself and only one of them. It's a functor only to one. Oh, the opposite. Only one of them have functors. So so this is the theorem, and so it means that also in the abelian world you can, to some extent, discuss the notion of free tensor categories generated by one object, but it doesn't mean it's this.
There's something that I don't understand. You first fix n,
Yes, this
And then
category
fixed.
is for fixed n. So you can use this theorem for fixed n. So you can take n to be a complex number, but if it's not integer, then this theorem is much simpler than just one category. And you can take it to be a parameter in relational functions, and it's also much simpler. You can try to take it parameter in the ring of polynomials, and I don't know what that's. I would guess that if you want to be a billion, you have to specify it further, but well,
Do we have a description of A?
they have a description. Yes, but it's not that simple. So the basic idea is to take some kind of limit of it. But it's not simple. I didn't put the paper. I probably listened to a talk about it, but not enough to understand the approaches. This is a hard one. So you don't listen. Let's see. 2003. No, later. Maybe 17. And go. So all the rest of this didn't do a thing in late 90s, I'm not sure. 90s. This So this was not the first example of such category without five factors. So the first example, so this kind of version of representation of GLN. So previous theorem was for representation of S, finite group. This deleted, so we also constructed them. But the representation of finite group is not free in any sense. So this should have been earlier example because this is a representation of this is like a free representation. What they did is just take representation of the group Sn and they constructed some other category that he called representation of group St, which is literally hard to construct. It's not free, so there is some more conditions. And again, for t not equal to n, so it's it's groupisation. So for t not equal to n, it's already a billion, and for t equal to n, it's not a billion, it's a Gaussian, but then it has two abelian numbers, so two options of abelian category. One is a representation of Sn, and another is, let's call it a head of Sn. And here we have this rep tilde of Sn. You have two functors like this, and any functor, there are only two options there. Any functor from this category to an abelian category, factor for exactly one. So this was before, and this already gives you an example of something with which have integer dimensions, but not super.
What's a rep head?
What?
What is a rep head?
So he constructed some category, abelian category. There's a in the functor like this, and any functor to abelian category factor to exactly one. It's like the analog of this A, yes. What it's saying here. So it's n abelian element, an initial object. Oh, not initial object, but together they kind of form initial object. The two categories of abelian categories, that's this. So, and these are the two. Okay, I think next time I will still continue my knowledge of category, but not for the 3 hours. Except we also want to talk about quantum groups and all algebra. But not too much.
So this theorem basically means that we need to add just one more category to this list.
It's
But
very
it's
much
a different type. So
it's not representation of any supergroup. So in this case, it's a type. It's kind of related to those guys because it's the limit of these guys. So I don't know how to whether it make you happy or not, but it's not like out of the blue. Related to this, but how to You can think about it as kind of like you add all the kernels and co-kernels to the Korean category. But you cannot really do it more or less in the same reason why you cannot really make a field out of a ring. Because when you make a field out of a ring, you take an element and you don't know whether it is 0 and then you should not divide by it, or it's not 0 and then you have to. And here is basically the same thing. So when you do these things, so you some of the kernels and co-kernels become 0 because the morphisms or everything, because the morphisms happens to be 0. And if you say that nothing is 0, then you want to consider all the kernels and co-kernels, and then you get there. So let's don't call it like this. Let's call it like heads. I'm not sure about this notation still than heads, or I don't know how they usually take it or not. So this category somehow we try to do these categories, but without. The idea is that when you go from here to here, you get larger and larger category, but they're larger in the sense that certain maps that was 0 before are not 0 anymore, because the kernels and co-kernels becomes object to it of dimension 0. But here object of dimension 0 is 0, and here not. And here even more objects of dimension 0. And when you add all of them together, you get this.
Wait, why did you replace A with
Because it just okay, that's okay. It's very single.
It's head?
Yeah. It's just a very single. It's a single category, so let's not give it a generic name. I'm not sure this is the correct name or the exact name, and I'm also not sure about it. They're all kind of friends of representation of GLN, but friends in some weird ways.
Okay, but should we think about this category as a kind of completion of previous?
It's completion of this one. Those are already kind of oblivion. You cannot complete them anymore. You can't add to them more kernels and co-kernels. But you extend them now. It's some kind of a.
But we have embeddings.
No, this is not embedding. From here to here.
Yeah.
Yeah, so it's kind of a leap. Code. But I'm not sure about in what sense exactly.